I'm Mario, and today I'm going to talk about how we do data science with Internet of Things on the edge at Hive. Let's start with a couple of definitions. Internet of Things is this recent trend of putting an internet connection into every device. The idea is that in this way, it can help you monitor your house or the car or even a train. And on the edge means that instead of doing the computation on the cloud, we move the computation down to the device. So let's see. How did I get here? So I started doing astrophysics, looking at objects like this, which are clusters of galaxies, and studying how they bend the light around them. And by studying this effect, we are able to study their mass and understand their compositions. And then at some point, I just decided I wanted to do something different, and data science was the obvious choice for me, because basically I would be doing the same thing I was doing before, just on houses instead of galaxy clusters. And actually, I went to S2DS, which is the event organized by PVigo, one of the sponsors of this conference, which helped me go from science to data science. That's why the name, and I definitely recommend if anyone is interested. So you might know the Hive thermostat. You probably are aware of other products that we make, like light bulbs, smart plugs, camera. You definitely don't know Hive Link. This is a service that can help you if in your family you have an elder person that lives alone. You can use our devices to make sure that they are fine and there's nothing happening, and everything is under control in their house. But we also make diagnostics for things like boilers, in this case, or the devices that detect leaks. And I'm actually going to give you a better explanation about this device, because that's what I've been working in the last year. So this is a leak sensor. Actually, I have one here. So the customer take this and attaches it to the pipe that takes water inside the house, and has two temperature sensors that measure the temperature of the pipe, so with this part here, and then measure the temperature of the ambient air around the pipe. And whenever we see a drop in the pipe temperature, so a difference between the two temperatures, we detect that means that there is water flowing. The problem with this device is that it has to be very cheap, which means that it doesn't have much power, computational power, and also it's powered by 2 AA batteries. So, and because of this reason, it keeps the Wi-Fi always off and only uploads data a couple of times a day. So it means that everything we do needs to be running on this device, and only if there is a problem, we can upload data to the cloud. Like you might wonder why doing Internet of Things on the edge. A good example of this could be the Amazon Echo. That has to record everything you say, has to listen to everything you say, because it's waiting for you to say the magic word. And it cannot send everything you say to the cloud. That's going to be super expensive for them. There's privacy concern. So what they do is they run a local model that just listens for the word Alexa. And when you say that, it starts sending that request to the cloud where they process your request. And the same for everyone interested in this space. The reasons are internet might not be reliable. In our case, our customers want to still be able to adjust their thermostat even if there is no internet. And if you think about it, running the algorithm on the device itself can reduce cost and speed up everything, because that's basically the ultimate parallelization solution. You are running, every device takes care of processing its own data. And also, in doing this, you can also enhance privacy, because you don't have any data. You can make sure that there's no data leaving the house. So how do we do this? We go through the standard data science approach. We collect data, we train a model, we evaluate it, and then we deploy it. Like, this is the standard data science approach. But every of these steps actually creates a new problem for us. Start before the beginning, collecting data. Real houses are actually really, really difficult. So what we did is just build a lab. So we have, in Leicester, we have a chamber with a lot of pipes and taps that you see here, and all of our sensors there. And we can control the temperature of that chamber. But actually, that chamber is within a larger chamber that is kept at a very low temperature to simulate the outside temperature. And we flow water from the inner to the outer chamber and go in a cycle so that we can simulate a real pipe bringing cold water inside a warm house. And this was really important for us because, first of all, it's a lab, so we control the environment, but also it allows us to understand the limitations of the product and understand the physics of the problem. But we quickly discovered that the lab cannot be a very realistic, can never be a very realistic representation of an actual house. So obviously, what you do, you take your device home. There's a saying which is, eat your own dog food or cat food, whatever. And that basically means be your own customer. So what we do is we take our own products home and we just use them like a real customer will do. So if I take a really long shower, I get an alert from the leak sensor because it says like, oh, you have been using water more than usual. But we also try to break them the same way that they would break in a real house. So turn off my router and I expect to get an alert from the hub, which control the other devices, saying, hey, there is no internet. Well, the alert will come from the cloud, which doesn't communicate with the hub. And it's really important because you, as someone developing a product, you want to know the product really well. You want to feel the same pain that your customer goes through when they use your product. But again, houses are difficult, and not all houses are different. People do different things, have different schedules. So next step is go to more people. So we give devices to everyone in our team and their friends. First question I ask when someone new joins is, do you know where your stop tap is? Because you're going to get a leak sensor. And basically, one of the best things you can do in this case is ask them to send you a picture of the installed devices and the environment around it. Because when you're sitting at your desk looking at the data and you see something weird, it's always good to have a reference picture, say, that's why maybe that's what's happening. And if you cannot figure out from the picture, what we do is just Slack them, because these are people in our team or are friends of them. Or we also send like an email. It's always really important to, at this stage, have all the information that you can have. But then it turns out that at this stage, the product is still not finished. Otherwise, we would have already released this to the customers. So when you give an unfinished product to your line manager or CEO of your company, you need to be careful, because it turns out that they actually the stakeholders in this project. And if you don't manage their expectations, if they don't realize that you give them an unfinished product that you are just testing or still developing, things might not go very well. And we actually have a joke in our company, which is, if you're a trialist, expect a cold shower. At some point, though, you need to go. We had to go to real customers. Again, everyone is different, and real customers will do unexpected things, like turning up the temperature of the house by putting the thermostat inside the fridge. And you cannot think about that stuff. You just need to go out and see what's happening. But also make sure that you have consent from your customer to use data from devices that they own to improve the product. This is really, really fundamental. But then now you have collected the data, and now it's time to build, to decide how good your model will be. And so we collect ground truth data like everyone else does. In some problems, the ground truth data comes for free. If you're trying to sell, if you want to develop a model to decide the price of a house, you can just find a database with information on the house and then the price of what those houses were sold. In our case, we don't really know the thermal properties, the heating properties of the house, and we cannot afford to send a team of scientists to every house, every trialist house to measure all of these things. So we end up doing, like I'm guessing a lot of you do, which is manual labeling. The problem in our case is that most of our devices rely on temperatures, and we need a lot of devices to collect the different type of houses. So we have a lot of data that we would like to label, but data comes slowly. Every day you can only collect 1 day of data from one device, and we need to observe a house for more than a year because we have seasonality and temperature changes with the different seasons. But the other big problem is that what we are trying to do, we work with devices and situations and systems that people don't normally think about. You normally don't think about how your boiler works or how your pipe works, how your pipes work. So we cannot just use common sense to label things. If you are doing object detection of an image, you can just pick any random person and have them click on an image. In this case, you need to understand the system before you start labeling. And so we end up just manually labeling all of this on our own, and which means that we actually develop an internal tool to view the time series data and label it. And this is a really interesting story because we did this just to be able to label data. And then at some point, we stopped labeling data because we decided we had enough data to start developing the model. And this viewer has actually become really very used by a lot of people in our team because everyone needs to access data. The firmware and hardware developer, they need to look at the data of devices sitting on their desk that they are still writing new firmware. Product or a trial manager, they need to access data for their customers, which are they are trying to help support and if they have any problem. And so it turns out that this tool, which was developed by us just to label data, actually became really important across the whole team. And actually, no one still really understand the benefits of this because it's an internal tool, and people will always tell us, oh, but how does this impact the customer? And you have to go through a couple of steps before you get to the customer. And this is something that's always tricky to justify. But sometimes, for some specific project, we actually found a way to automate the data collection. Raspberry Pis are really cheap, sensors are really cheap, and we just put together some very simple things and attached it to pipes or whatever we were trying to do, and just automated the data collection. And this is a solution that doesn't scale really nicely because you will have to, we had to have this Raspberry Pi just go around the whole team to collect a couple of days of data for each of us, but it did the job. The other option that we sometimes go through is if we realize some of this problem at the early stages of the design, we just design the product hardware differently so that it does the job through hardware instead of doing algorithm. I think a lot of us are very lazy, that's why we program things, and if I can do something in hardware, why do I need to develop an algorithm? So now we have the data, we know how to evaluate our model, and let's see how we deal with a limited computer. So the leak sensor, it's very, very limited. Has 32 kilobytes of RAM, very limited disk space, and there's no operating system, no file system, as runs on a Wi-Fi, and it's powered by 2A batteries. And I think about this as a 20 years old device. Now, some of you might say, oh, but my Pentium 1 or my computer from the 90s is more powerful than this. But your Game Boy was not. The Game Boy actually turns out has very similar specs to the leak sensor. Apart from the processor, it's this thing here is much faster. So how do you take a modern machine learning model and fit it into a Game Boy? It's going to be hard. But on the other side, the Game Boy managed to run Pokemon Silver, so you should be able to do something. So our goal is to do this, right? Our goal is to prove that our machine learning model can beat the existing heuristics that we had in place. And we always start with simple heuristic, because that, first of all, gives us a benchmark or something to beat. But also, as I showed you already, we need to get as fast as possible to real houses. So we want to have some model running on the device when we just start our trials. And so we start from this. We start from already a model existing there, and we want to show that we can beat it. So which means that we don't need to actually worry about the constraints of the hardware. We just need to prove that this is doable, because at the end of the day, you don't know this. You don't know that this machine learning model is actually better than whatever we have in production. And also, when you write with low-level C code, you need to worry about all of this stuff. And these are all the reasons why I use Python, because I don't have to deal with all of this. And again, so it makes us go faster it makes us progress faster. And if there is a problem, because we are iterating faster, we can find it earlier. So we do this, and we end up with a nice machine learning model. But this model is above our performance requirement, but it's just too complicated to fit within this device. And so you sit down and you think, okay, how can I improve this? And you find some way maybe to represent your model differently, so it's still the same exact model, but it's a more efficient way of writing it. Again, we are lazy programmers, so we just do things fast to get to something, and then we worry later. I will always let future Mario worry about past Mario. But then, at some point, you need to make some compromises. And I think about this first stage as lossless compression. You just rewrite the model, but it's still the same model. But at some point, we have to do some lossy compression. And so we start to remove pieces of the model, and we think, we realize, in Python, everything is a float. Every number is a float, is a 64-bit float. Do we really need 64-bit? Can we do it with a 4-bit integer? Can we do the same? And that's where that ground truth and those labeling becomes very useful, because we can start taking away pieces and changing some pieces of the model and monitor the performance and see this point moving down. At some point, hopefully, this model will cross the complexity requirement, but still be above the performance requirement, and that's the model that we deploy. And so then you go and deploy it. Job done. Thank you for listening, and no, that's not really how it works. Because your device is not a server in your cloud. Customer can do whatever they want with the device. We actually, I took this picture this morning, obviously, but this actually happened from one of the people in our team. So we had to develop a model to detect bad installations. One of the things that people do is no one understands pipes in their houses. Like, why would you? So you go to install this, and there are 3-4 pipes, and people are doing this online onboarding on the phone, and I just want to get this done. So just put it on a random pipe. And it turns out that one of those pipes can be a hot water pipe. And so we have this model to detect hot water. So one of the people in our team, they wanted to help. So they said, oh yeah, I didn't get the alert of the hot water installation, but I put it on the shower head. And I thought, yeah, maybe that's true, but what we are trying to detect is hot water coming out of the boiler directly, and not on a shower head, which is probably made out of plastic. So customer will just do whatever they want. But also, it's tricky because if you have a problem or a bug in your software that takes the device offline, how do you know what happened? Because the device is offline. It's not going to send any more data for you to troubleshoot. And how do you fix that? Anything you do will affect the customers, and they will be the one fixing your mistakes. You cannot just delete the instance and rebuild it. You will have to send out emails or do whatever you do to ask customers to change batteries or to factory reset their devices, and you don't want to do that. Every time you release a new firmware, you risk draining the battery of your device because the device has to download a large image and process a lot of stuff. And then you always risk introducing new bugs with every over-the-air update. So the sad part of this is that we don't have any solution for this. Doing firmware, doing hardware is really difficult, and the risks are great. You cannot fix problems that get all the way to the customer. You have to bother the customer and have them fix those problems. So you just have to sit down and go through all the steps. You need to, when you have a new firmware, you need to release the firmware to QA, and then your QA testers will try and hopefully catch most of the bugs. And then what we do is we release this new firmware to the devices we have in the lab, if that's a new algorithm that we have developed, because we want to test it under control conditions. Or for example, if it is a firmware that has to do with connectivity, we release it to our team members, because we want to see how that firmware behaves with different type of routers or conditions like apartments where you have 20 Wi-Fi in range and the device might be confused. And when we see that that works, we move to the next stage, which is this extended group of trialists. And finally, we get to the customers. That model that I briefly mentioned took us 9 or 10 months to go through all of this, because we kept finding problems with firmware and going back to square one. So in the meantime, we had to find something to do, just to wait until our model get to production. So what have we learned about this? Get the product out there as soon as possible. There's no way you can think about every single scenario. You need to get it out and wait and see when it breaks. And be prepared for that. Work very closely with the whole team working on that product and be able to react to any problems that will definitely arise. And do everything you can to get ground truth data. This here is the single most important step in your data science pipeline, in your data science work. That is what allows you to build a model, to know for sure that your model works. And in our case, for example, that's what allowed us to just be able to fit the model inside the device, because we were monitoring this. And you could delete your trained model and just retrain it if you still have the ground truth data. So that's really the most important part of everything. Just do whatever you can. And also, initially, don't worry too much about your limitations. Keep them in mind, but don't worry, because you want to iterate fast. You want to find the problems as soon as they arrive. And finally, don't skip steps when you're releasing, because firmware is hard. And I find interesting that most of these actually apply to everything, not just IoT. on the edge applies to everything. So I don't know. Feel free to borrow them or just don't, whatever. But yeah, so this is it. If you are interested, get in touch with me or with Miroslav, the head of data science. And thank you for listening. Questions? There's a mic down there. There was just shout, otherwise.
Hi. So I think you mentioned at the beginning that this could be used for elderly people. So if it's connected to the internet, I mean, is there a requirement that elderly people would have to have Wi-Fi in their homes?
Yeah.
And is this a practical limitation?
Yeah, no, exactly. So that's why not a lot of people are aware. We are still slowly building this. You can just go on our website and see all of this. The idea is that this will notify a circle of people, family, things like that. So you need, in that case, you need an internet connection to alert people. But that, again, when you need to alert someone, you need an internet connection. There's no way around it.
Yeah, sure.
Thanks for the talk. So did you say at the beginning that the purpose of the device was to detect leaks? So I was wondering, in your training group of like the people at your company and friends, I guess you don't have many leaks that occur in that time. So how do you deal with that sort of that sparsity of sort of positive cases?
Yeah, so it's actually interesting because the aim of the product evolved with time, and so we ended up with redefining a little bit our requirements. So even though it's still called leak sensor, it's also very good at detecting any usage. So we basically have a boundary of just a duration. So even though sometimes real leaks are rare, we still label a lot of things that are probably not leaks, are people washing their car or things like that. And that actually increases the frequency, and we didn't worry too much about this being an underrepresented class, because it turns out that if you include this, then you end up with it's not a huge problem anymore.
So you include usage as a detection of a leak?
Yeah, because from our point of view, we just see water flowing. We have no way to distinguish between the two. So we only put like a time limit. So in the app, you can say, alert me if I see water flowing for more than 15 minutes or 60 minutes. It's a very limited device, and so in that case, again, this doesn't become a problem anymore, and we just didn't bother with it.
Hi. So what's the need to have so much computation on the device itself? Like what model are you building that you couldn't just push the data to the cloud and then have alerts generated all in the cloud?
So it depends on the product. For example, for the leak sensor, because it needs to be cheap, it runs on AA batteries. You also don't want to have something wired that's also connected to your pipes. And that means that we cannot leave the Wi-Fi on. It has to be always off. And so if there is a leak, we need to be able to detect the leak when the device is offline. We cannot wait for the device to wake up, sense data, and then 6 hours later detect the leak.
So do you end up fitting every customer ends up fitting a different model for their
we
house?
thought that might have been a plan at some point. We actually have, the model itself is global, but one of the features that go into the model is learn for different customers.
When you were training your model in the cloud, when you just had to detect the usage, you said you had to manually label because there was no data from homes. And I was wondering if you had access to the data from the smart meters that they had. I don't know if you would. Then you would potentially be able to correlate the two. That's it.
Yeah, so that's something that we thought about a lot. And the problem with smart meter data is just the frequency at which the data is sampled. And so that's just too large for us. The device collects data much faster than
I see.
anything like that.
Okay.
But yeah, it would have been like it is a good ground truth for us for.
Question. So you mentioned a lot of the times that you went back and forth between development and QA. So apart from the issues that come from actually developing a firmware, which like it's a task of its own, how many of it was related to prototypes done in Python, then converted into C, bugs in the process, go back and forth?
So I'm guessing that before my time in this project, there was a lot of that. I worked on this for a year and a half, and there was only one time where we were the reason why we had to go back. But otherwise, it was mostly a connection problem. But yeah, there was another part of your question. I think I had something.
No, this was the question basically.
Yeah, again, it's at the end of the day, the model is actually not super complicated, and we do have data, historic data, so we just try to do. Oh yeah, sorry, I now got it. So one of the things that we did to make sure that our model was actually implemented correctly is that we produced, so what we do is we develop the model in Python, and then we hand over the model to software engineers to implement it, if it is in the platform, or in this case, in C. And actually, I call this different person, but actually the software engineer was actually a data scientist who know how to write C. And when we do this, we actually produce unit tests that are the input and expected output from the model that we have trained. And so with this we make sure that what is implemented either in the cloud or on the device is what we have trained. So we know
So similar process to shadowing models. So you put them side by side, and then you check that the outputs are the same if the inputs are the same.
It's just done kind of offline or on unit test. It's not done in.
Bonus question: how long does it take to go from Python to C, from a Python prototype to a C production model?
For this particular model, it didn't take too much. Stack Overflow is always near. No, seriously, like that's what we did. We just Googled how to convert scikit-learn to C. And there was something it's like, okay, that works. But yeah, obviously, you test things, and we tested every step. We tried to compare input and output and make sure that everything was how we thought it was.
So I was wondering, was the hardware design frozen, or did you have any sort of feedback into that?
Sorry, can you repeat?
The hardware design, the requirements for the hardware, were you able to define your own requirements, or
So for the hardware, you mean?
No,
sorry.
for the capabilities of the hardware, as in available memory, processor, kind of sensors.
I'm not sure. There is definitely feedback, but at this stage, the product is a little bit mature. So we kind of, for this specific product, we were given that. But we're actually thinking about new additions, and we are involved a lot with that because we have this lab, so we can go and try the new hardware there. So we try to keep everything, like the whole team, very close and involve everyone in decision making.
Thanks for the talk. I thought it was really interesting. With a sensor and hardware this small, do you start having, do you have to have security considerations even for a product this small, or does that happen later?
You always have to have those, because at the end of the day, even though this model runs on the device, we still send data to the cloud because we want to make sure that everything is working. So you always need to be aware of everything. Some people might think, oh, but my temperature is not sensitive, but it's everything you do in your house. It's your own business, and everything should be super secure and protected.
Thank you.
I don't know if the next speaker.
How do you deal with connectivity issues if the device is in the basement, for example?
So we ask the customer, is your stopped up in reach of the Wi-Fi? They can always say yes, and in that case, it doesn't work. again, when you have a product that requires that is built around notifying someone, you need the internet connectivity. There's no way around it. I think. Yeah. So, is it?